So here we're going to start on a class of policies based on value function approximations. This is our third class. It turns out value function approximations is a very rich and complex method for constructing values. So I've divided it into 5 separate parts. This is part 1. And part 1 is I'm basically going to do an introduction to dynamic programming, effectively Bellman's equation. So I'm going to begin with classical exact dynamic programming because it's important to have this foundation. So my modeling framework, as you've seen before, we have states and I do it in a finite time horizon. I'll come back to that. So ST is the state at time t. We have a decision X, which is determined by some policy. Often I don't put a time index on the policy, but sometimes you might. Sometimes people will say, oh, I'm going to assume that time is captured in the state variable. It's fine. I don't really care. The exogenous information process starts at time 1 because the first time interval is time interval 1, and it's best to think of information as arriving over the time interval. Each WT is often a vector because there's different sources of information. In fact, it's a vector of functions because each of these can depend on the current state and or the decision that you've just made. Then we have a transition function that if you tell me what's in the state variable, make a decision, then you observe the exogenous information, the transition function will tell you the state at st plus 1. Then we write out the objective function where we're optimizing over policies. Right now we're focusing on value function of policies, but we can do cumulative reward, we can do final reward, it doesn't really matter. I'm going to generally as a default go with cumulative reward. Quick reminder here, why dynamic programming is so hard. If we start off with what we know now, maybe you have an asset that we can buy, sell, or hold. That's our initial decision. Then new information comes in. The price may go up, down, or stay the same. Then I make another decision, more information. And this tree process explodes with such dramatic speed, even this toy problem becomes very hard. And this is an utter toy problem. Go to anything more realistic. I mean, we have problems where x's are vectors, and I can't even enumerate all the possible values. Bellman's breakthrough was to say, let's just assume that the state variable is discrete. Now, once you insert that little assumption, and of course I'm not going to assume that there's a trillion states, let's assume it's an amount that I can compute because I'm going to have to compute the one-step transition matrix, which is dimension the number of states by the number of states by the number of actions, and each one of those elements is itself an expectation over the random information. Anyway, let's assume I start in some square state, some initial state, and I can make any sort of decision. Those are the solid lines. And then I can have any kind of random information. I really don't care. Actually, the decisions and information there could be quite complicated here because once I come back to the state variable, the pre-decision state, it's discrete. And it has to fall in one of those discrete boxes. Once again, make any type of decision, observe any type of information, but if you have discrete states, the system always comes back to one of those discrete states, and that's what prevents the explosion. So just by making that assumption of discrete states, we no longer have that explosion, even for relatively large problems. Okay, so let's start off with our optimization problem of coming up with the best policy. In this section of the talk, I'm going to come up with an optimal policy if I could compute everything. Now, the optimal policy is that second equation. It's the argmax of the one period cost or contribution, let's say I'm maximizing, plus everything that happens in the future, which means all the decisions I'm going to have to make in the future with all of the random information. Now, let's take everything going on inside that blue circle and realize that's just a function of the state at time t plus 1. Okay, so let's just call it Vt plus 1 of St plus 1. That's just a function. Remember, with Bellman, St plus 1 is discrete, so that's not necessarily a very complicated function, even though it looks complicated. Now, so my optimal policy, that fourth equation, I can write out fairly simply, and that boils us down to what is famously known as Bellman's optimality equations, the last equation, where on the left-hand side, I have the value of being in the state st at time t, which is a function of the value of being in state st plus 1 at time t plus 1. Very elegant, compact equation if I could only compute it. Now, so the way we can compute it is we're going to go backward in time. I'm going to start off with some ending value. I'm going to say, okay, at the end of time, let's just assume all the values are 0, or whatever you want to assume. Now, let's assume that I can compute the one-step transition matrix. So if I'm in state st and have action xt, I can compute the probability of landing in state s prime. Remember, that has to be discrete. If I can compute that, I can say if I know the value function at any time t plus 1, which of course I'm assuming I do at time capital T, I can compute v star of t. So this was a holy smokes, this is amazing. We've cracked the sequential decision problem, the Markov decision process. So the optimal policy does nothing more than take the v stars, plug them in that argmax that we had on the previous slide, and I'm done. So this was considered a major breakthrough. The problem is that this equation is limited to the smallest of toy problems, not even small problems. It has to be toy problems or problems with very special structure. Okay, so dynamic programs that can be solved exactly is, well, let's say you do have one of these discrete state problems where the number of discretes is not too large. By the way, the action space pretty much has to be something discrete so I can sum over it. And finally, there's a random variable in there, and I need to be able to compute its expectation. So we're going to also hope that that's not very complicated. In my book, in chapter 14, I have some other problems that have very special structure, one called the gambling problem, one called the continuous budgeting problem. There are these highly specialized problems where you can sit down, take the expectations, they're very simple, solve the argmax because you're probably taking derivative and setting equal to 0. Now, a really major problem is called linear quadratic regulation. This problem is generally ignored in books on Markov decision processes, but you're going to see it in every single book on optimal control because it's very big in engineering. This is where you have, by the way, this is where you have continuous decisions, and they can even be a vector. Usually it's a small vector, but it doesn't have to be very small. The objective function has to consist of maybe a linear term and a quadratic term, nothing else. And the decision variables have to be unconstrained. I can't have any sets of constraints. If you have that problem with a lot of algebra, and it's a tremendous amount of algebra, you can boil the optimal policy down to a linear, a function that's linear in the state variable. So this was considered a major breakthrough. It actually has real-world applications. And so this is one of those very special cases of problems. So let me talk about the 3 curses of dimensionality. I'm going to take an energy storage problem where I'm bringing energy from a wind farm or buying it from the grid to meet the load of, say, of a building or a campus or a city. And then I'm going to have some battery that I can use to absorb to smooth out the variations. Now, I have a set of 4 equations to handle the dynamics of the problem. I'm going to have 4 state variables. The current level of wind that evolves according to some stochastic process, the price of the grid, the demand in the building. Now, the R variable, that's how much energy I have stored in the battery, and that's an inventory problem, which does depend on X. So that's a controllable system, and everything else is just some exogenous random input. So if I write out Bellman's optimality equation, I have a 4-dimensional state variable, a 5-dimensional control variable, and a 3-dimensional exogenous information variable. I call this the 3 curses of dimensionality. This is my book that came out in 2011, was the first book to focus on, because in dynamic programming, everybody talks about the curse of dimensionality, and they're talking about state variables. But actually, there are 3 curses, and they all matter. Now, let's imagine the state variable is a scalar, the decision is a scalar, and the random information is a scalar. So looping over all the state variables, let's say there's 100 possible values, then there's all the possible decision values, maybe there's 100 of those, and then maybe the W variables, there's 100 possible values. Because these are nested, you have 100 times 100 times 100 all inside an outer loop over time. So this starts to get ugly, but wait until you make those vectors. Now the state variable is 4 variables, and these have to be looped over in 4 nested loops. the decision variable is 5 nested loops, and the exogenous information is 3 nested loops. You can see how quickly this is exploding, even for a relatively small problem, which we're looking at here. This is just not computable. Now, let me finish this segment with a brief comment about steady state problems. It's my theory that when Bellman first solved the problem for finite horizon, assuming you can compute the one-step transition matrix, it sort of looks trivial. The finite horizon problem is just backward dynamic programming, and you're done. Move on to another problem. Everything's solved. But what if you do an infinite horizon problem? Now look at the equation. I don't have t anywhere. I have this function v of s, the value being in state s, on the left-hand side and on the right-hand side. That's the same function. So now I have to find what is called a fixed point. And so how do we do this? So this is an interesting problem. Turns out a fairly simple algorithm for it is start off, set all the v's equal to 0, maybe some other value, but it doesn't matter. It absolutely doesn't matter. Now take your vn, let's start off with n equal to 0. So on the right-hand side, I know vn, so I can compute this. So let's loop over all states. There you see us looping over all states again. I can compute vn plus 1. Now you increment n, put the vn plus 1 over on the right-hand side, and do this again. This is an absolutely convergent algorithm. It has provable bounds, tight bounds, beautiful, elegant theory. Of course, you have to be able to loop over all the states, and you have to be able to compute that one-step transition matrix. But this has ended up being the default notation. Now, there's this really elegant theory, beautiful bounds. I used to teach this material. It's all covered very elegantly in Putterman's book on Markov decision processes. It's great classroom material if you have students who are reasonably sophisticated mathematically. It looks great. It's just not useful for anything, okay? Because you can't actually compute any of these. Now, one of the things that you have to realize is that the reinforcement learning community in computer science picked up on this notation. So if you go to any reinforcement learning book and look at the notation, they've adopted the notation of steady state. So you will never see state variables with a time index on them. Now, I do a lot of real-world modeling, and I have never run into a problem that I can model in steady state. I just don't find them. I think this is a mathematical curiosity. If you go over to the books on optimal control, which comes from an engineering audience, everything's in finite time. So it's very odd because when you model real-world problems, you really do need to model the time variable. But computer scientists don't do this. And if they do need time, they'll say, oh, I just buried it in the state variable. So this is a little bit of the history of why reinforcement learning, you don't see time in the state variable, whereas if you look at any of my modeling, I always have time. So there's more on this material if you just go to the website, warrenpowell.org, go to policies and value function approximations.